Hello everyone, this is Ankush Sharma here. I shall be starting in the next 5 minutes. Please let me know if my voice is clear and everyone can see my screen. Thanks, Mr. Stanley. I shall be starting in the next 5 minutes, so I believe that everyone can hear me and as well as can see my screen. So, hello everyone, this is Ankush Sharma again. So here we are with the third educational webinar in MIDAS GTS. Today our education webinar is on deep excavations. So will be mainly a demonstration where I will be discussing a project, and at the end of project we shall be talking about the question answers. So here we begin. The workflow in which I will be following today is, first I will discuss the project overview, on which we are going to perform a deep excavation, and then the project features, and then which is mainly the demonstration part, and then lastly talking about the post-processing results. Taking care of every nuances you need to take at modeling, even at meshing, and as well as while seeing the results. Not that you see some colors, that is the actual results. No, you have to figure out some ways to get the actual information, to extract the actual information from millions of elements. So today I will be performing a semi-coupled deep excavation, by which I mean I will be performing stress analysis on deep excavation, as well as also perform a dewatering on this deep excavation, which means this ground which is there in front of you, this plan will be excavated in 3 layers: excavation 1, 2, and 3. And along with that, initially it has a nodal head of say 40 at the top, nodal head of total head of 40 at the top, and which will reduce and level as we proceed with the excavation. So this is a very important feature when it comes to real time geotechnical projects, because in that case the ground is not dry, so you need to take care of the pore pressure that is there, that is existing in the ground. So you need to perform a dewatering analysis. In short, you need to perform a semi-coupled analysis. So here I am with the solution. So the dimensions of the ground, as can be seen, are 40 by 40. We will excavating the ground in 3 layers. Again, as I said, 5 meter depth of each. We will be having piles. These piles will be modeled using linear, using 1D beam elements, not the pile elements which is which is present in GTS. That will be demonstrated in some coming educational webinars. So here we try to model the pile using the beam elements. Along with that, as we perform each excavation, the retaining wall will be installed for only that portion of the excavation, and it will be strengthened using some wales and struts. So this also includes the modeling of wales and struts. As can be seen in figure number 3, we have the piles at the edges. These piles are the H piles because the section is I section or the S section. The struts will be again modeled using truss element, and this will be round in shape, and the wales which are and the wales will be rectangular in shape and will be modeled using beam elements. We will model the ground using solid elements, since we won't be applying some of the very hard external loading. So I think in this demonstration I'll be going with the 4 nodal tetrahedral solid elements for to model the ground, and the wall will be modeled, the retaining wall will be modeled using the plate elements. So again, concluding the project features, the ground layer will be excavated in 3 layers, 3 steps: excavation 1, 2, and 3. Dewatering is performed before each excavation. So the concept is, in the original ground, you first install all the piles, and then you perform a dewatering for a particular depth of the layer, and then you excavate, that layer. This is one way. The another way is you just excavate the layer, and the dewatering will be performed by itself. You don't need to perform an external dewatering using some of the pumps or something, some external devices to extract water from the soil. So here I will be using the first technique, where you have to dewater the soil first, and then you can excavate. Coming over to the project features again, and impermeable. I will focus on this word impermeable. retaining wall is installed with each excavation along with struts and wales, which are the structural elements in this case, to strengthen the wall. By impermeable, I mean the water cannot seep through the wall. So when you install a wall, you have to install some of the seepage faces with nodal head 0, or you have to think about some of another tactics so that you don't have any inflow through the from the soil through the wall. So this we will be seeing in some time in the demonstration. Lastly, a construction stage analysis sequence which we'll be following is you perform a steady state seepage analysis, which has to be followed by the stress analysis, which is a very general feature of the so-called semi-coupled analysis. And then the H piles are installed. After the H piles have been installed, for each excavation, you dewater the soil and excavate the ground, activating the structural elements which are walls, struts, and wales for the each excavated portion. And this has to be followed for all the 3 excavations. And then at the end, you need to ensure that after you have excavated all the material, the bottom has 0 pore pressure, which means you don't have any water lying in there. You have to remove that water. So you have to take care of that thing also, which again we will be talking in our demonstration. The workflow which I'll be following for the demonstration is, first we'll be defining the material and the properties for various elements we'll be using, either the solid elements, the linear elements, or the 2D plate elements. Then moving ahead with the modeling, and we will discuss some of the modeling techniques, some of the cheat codes with which we can actually cheat the time and then go ahead with the modeling. And then further we'll be creating some of the meshed elements, either 3 nodal triangular elements for the plate and 4 nodal tetrahedrals for the solid ground. Finally, we'll apply the boundary conditions, which are nodal head, the ground boundaries, and the pile boundaries, and then seepage faces to review the boundary conditions, to review the portion, to review the you can say to review the boundary condition as you excavate the soil. Further, you will be applying the loads, then defining some of the construction stages, and lastly, we will move to the results. So let's begin with our demonstration. No. So as I said, the first thing will be defining the attributes, defining the materials, and defining the properties. So here we begin. We can add a new attribute. For ground, we will be adding a solid attribute. For piles, for struts, for the base, we'll be adding a line attribute, and for the wall, we'll be adding a plane attribute. For now, I'll be importing the attributes from a previously defined model. So as I said, the ground will be added using solid attribute, the piles will be added using line, struts, line, wale, line, and wall will be added using plate attributes. So let's see the properties and the materials we have used to define these attributes. The ground has been defined using Moho Coulomb. When we deal with deep excavation projects, sometimes loading, unloading can be a problem. So for that purposes, when you have to deal with such a great amount of loading and unloading, MIDAS GTS also provides modified Moho Coulomb, which removes the limitation of Moho Coulomb with regard to loading and unloading. Next, since we are performing a seepage analysis, the permeability coefficients or the hydraulic conductivity coefficients are very important. So we need to ensure that the conductivity is very low. if it's not as low as it's not as low as clay, but it's of moderate fine sand. So I have defined the permeability corresponding to sand. A water content of 0.5 has been used for this demonstration, which can be changed, and other material properties can be changed depending on the soil conditions present at the actual excavation site. And for the structural elements, an elastic constitutive model has been used with a high elasticity, with a high modulus of elasticity. And this structure material will be used for piles, struts, and wales. Similarly, for the wall, again an elastic constitutive model has been used with a high elasticity, modulus of elasticity, which can be used depending on other von Misers also. So this was all about the materials which I will be using to for the various elements which we'll be creating in here. Next is defining the property. The H piles have been defined using the beam elements. As I previously also emphasized, that here we will not be dealing with the pile element which is provided by MIDAS GTS. With pile element, you can automatically take care of the nodal connectivities that we will be discussing in the coming education webinar. But here with the beam elements, you have to take care, you have to be very conscious in modeling so that there is nodal connectivity at every point. So this pile element has been the section element for the pile is I section, and the properties have been defined for this I section. This kind of pile is called H piles. So the struts, as I said, have been defined using truss elements, and a solid round type of section property has been defined for the truss. The walls, the wales have been defined using beam element, and a solid rectangular section property has been used for the wales. Lastly, the walls have been defined using plate elements, which are plane stress elements with a thickness of 0.01. For now, we perform the analysis with the output coordinate system of element coordinate systems, and in the later part, when we visualize the results, we need to play around with output coordinate system, which I'll be showing in some coming time. So this was all about property and its materials, and in short, the attributes of the materials which we'll be creating. So here we begin with the modeling. So first we need to create a 2D rectangle to represent the ground. The ground has dimensions of 100 by 40 in the elevation. So we will define a rectangle of 100 by 40. The whole modeling I will be doing corresponding to the images which I have shown in my presentation. So the next part is, so this this line, this wire is we will use this wire to extrude the ground. Now the next part is, we will similarly make a 2D frame for the excavation layers. But before that, we need to, as we see that this curve can be created on the work plane. So we need to move this work plane perpendicular to perpendicular to the height of the excavation layers. So in short, we'll use a 3-point plane to move the work plane. Specify the origin XX. So here we have shifted the work plane to another level. The next step is we will be specifying the 2D framework for the excavation layers. So as as we see that the excavation is situated at a distance of 20 meter from the edges and has a dimension of 20 by 40. So similarly, we will be providing those dimensions in here. So here we are with the 2D framework for the excavation. So we will use this 2D framework to extrude the excavation layers. The next point is, let's model the piles. So for piles, the trick we'll be using is, we will first create a point, we will then translate that point to the required depth, and then we will create a 3D element. To create a point, I will be using the curve interaction. Now translate this point to the required direction, in the required direction, and the piles are going to be of the length of 19 meter. So we have copied a point at a distance of 19 meter from the original point, and now we are going to use a 3D line to make the pile. I think so we have made the pile. The next we'll be doing is, we will be copying this pile to the required distances as can be seen in the image. Along the length of the excavation layers, we'll be having piles at a distance of 5, and along the width of the pile we'll be again having 4 rows at a distance of 5 meter each. So I will be translating now this set of piles to the another side of the excavation layers. Next, we have to create the piles for the sides also. So here we have created all the piles required in our deep excavation project. The next step is, we need to model the studs, and then we need to model the wales. So for the first step, we will be using a 3D line feature of GTS to create the studs. Just connect the points where you want to create the studs. I'll be copying this line to the required distances. So we have created the struts also, but these struts have to be placed at a required distance from the top, which we will shift after creating the meshes for these struts elements, and then we will shift those meshes to the required distances. The next step is, we need to extrude the ground. We need to extrude this 2D framework to represent the excavation ground, and then using some of the dividing surfaces, we are going to make the excavation layers. So here comes the trick. If we just extrude this wireframe, select the wire and the selection filter. If I just extrude this wireframe in the required direction, we are not going to have the impression of these piles on the solid created. So which means after the solid is created, we need to imprint those piles on the solid to ensure the nodal connectivity. Or there is, if let's see, if we don't imprint if we don't imprint the piles on the solid, what's going to happen? So look what we have created. There is no impression of any pile on this solid, which is not okay, since there is no nodal connectivity between the piles and the solid created. So we revert it back. Let's hide this thing. What we are going to do is, I will first intersect this wireframe with the piles, so that all the piles will have the impression in terms of a point on this wireframe, and then I will make a wire again from those intersected curves. So the newly made wireframe will have the impression of each pile, and then I will extrude that wireframe to represent the excavated layers. So here I go again. As I said, first we intersect the wireframe with all the pile elements. Doing this, we have the impression of the piles on this wireframe. Next, since we are going to use this wireframe to extrude the excavation layers, we'll make wire from the intersected curves, but we don't require these trusses edges, so which has to be deselected. Using a multi-entity method, with this thing, the actual imprint of each point on this wire will be retained. If we use single entry, that impression won't be retained. So it is very important to use multi-entity method. So we have the wireframe with us. Now we will extrude this wire to the required depth to represent the excavation layer. The excavation layers have to be extruded to a length of 15 meters, since 3 excavations have to be done, and each the depth of each excavation is 5 meters. So let's see. So let's see again. Now each pile has its impression on the solid created. The next step is, I will extrude the ground to the required dimensions, and then we will embed this solid representing excavations with the ground. So again, generator feature, extrude, change the selection filter to wire, select the extrusion direction, specify the length is 60 meters, apply. Since we see that the portion is overlapping, so we need to embed this solid representing excavation layers in this ground. So model solid embed, tool object is excavated ground, and here we are again. Now the solid is embedded in the ground, which is very important, so that we don't have overlapping solid materials at one place, because if we have those, there will be problem with nodal connectivities as well as creating mesh elements, as this may result in some of the free faces. The next step is to divide the excavation layers. So we need to divide the excavation layer in solid in 3 layers. Excavation layer 1 of depth 5 meter, excavation layer 2 of depth again 5 meter, and same for the third layer. But we have wales at a specified distance from the top. The wales are at a distance, the wales and struts are at a distance of 4 meter from the top. So which means for now we will have the dividing curves at 4 meter, the next at 1 meter, again at 4 meter, 1 meter, and 5 meter. Doing this thing, the motive why I'm dividing the whole excavation solid in 5 layers will be reflected in the coming demonstration, because this is a so-called cheat code to which I'll be using to model my whales, and as well as ensuring nodal connectivities between the piles at the later stage where we'll be meshing. So going back to the model again. So we'll extract a edge from this wire, translate that edge in the required directions at the specified distances, and then we will extrude the created edges to have our dividing surfaces. So let's extract an edge from this wire. So we have a extracted edge. Now we are going to translate this edge in the required direction. We will have a non-uniform copy at a distance of first 4 meter, then 1 meter, then 4 meter again, 1 meter, and lastly 5 meter. Now we have the edges at the required places for which the dividing surfaces have to be created. Using these edges, you are going to create you are going to extrude the dividing surfaces. So geometry, generative feature again, extrude. Change the selection filter to edge. Select the extrusion direction and say it has a length of 70. So using these dividing surfaces, I'll be dividing this solid into the required excavation stages. So solid, geometry, solid, divide. So divide this solid, the tool surfaces. This is again a very important feature when it comes to modeling, because dividing touching faces of the neighbor, we have to select the ground as a neighboring element to ensure that each dividing on the curve created on dividing the big solid into the required excavation layers have proper impression on the neighboring ground also. With this thing, we can ensure that there is nodal connectivity and there are no free faces, because if there are free faces, we won't be able to proceed with our analysis in the later stage. So here we are. Let's see what we have done. For convenience, I have changed the display mode of the ground to wireframe. So we can see that the ground has been divided into, the excavation ground has been divided into 4 layers: D1, D2, D3, D4, D5. D5 and D4 will represent my first excavation, because the total depth of D5 and D4 is 5 meter. D3 and D2 will represent my second excavation, and D1 is going to represent my third excavation. So the next step, so as we see that till now we have modeled our struts, we have modeled our excavation layers. The next step is to model the piles. We have modeled the edges for the piles, and we have created the impression of those piles on the excavated layers. So the next step is creating whales. Whales I won't be creating in here. We will be using the extract function of MIDAS GTS to model whales, as well as to model the retaining walls. Again, extract function will be used to model the piles. We have only created the impression of those piles on the embedded solid, but we haven't actually modeled the piles. By modeling, I mean we haven't created 1D elements for the piles. We have just created the edges for the piles, and those edges have been the impressions of those edges have been created on this on this excavated solid. So then let's move ahead with the meshing part. We always prefer a meshing from in to out, by this I mean we always mesh the smaller elements first, and then if we are using the auto mesher, if you are using the map mesher, by which you create 6-dimensional or 12-dimensional hexa solid elements. By that method you actually control the every meshing. You actually map each element you want to model. But using auto mesher, with the help of which you create 4 nodal or 8 nodal, if you go for higher order meshing, creating 4 nodal or 8 nodal tetra solid elements, in that case you always start from in to out. You mesh the smaller elements first, and the auto mesher automatically adjusts the nodal connectivity and the size of remaining elements as you move from in to out. But if you do the vice versa, moving from out to in, there can be a problem with the meshing, because the the required size of tetrahedral element might not be created. So let's start with auto mesher. Auto mesh solid. Element size is going to be 2. The attribute of these excavation layers will be same as that of the ground, so which is ground. This is going to represent my excavation layer 1. And if we want to, with this option till now, I have ensured that I will be creating 4 nodal tetrahedral solid elements. But if I want to create higher order tetrahedral solid elements, all I need to do is generate mid-side nodes. And this ensure that we have more nodal connectivities, and in short, we have more accurate analysis. For now, since we are, for this demonstration, I'll be preferably using low order tetrahedral elements. View it and apply. So this was my excavation 1. This is that these 2 solids are going to represent my excavation 2. And lastly, I have excavation 3. The excavation layers have been meshed. We have created solid elements for these excavation layers. Now it's a turn of the ground. We have to create solid elements for the ground also. Since analysis will be more concentrated in this area, we can have a big element size, say 6 or say 5 for the ground. And as I said, with auto mesher, the program automatically adjusts the size of the elements to have 2 element size on the inner side and have 5 element size on the outer edges. So this is my ground. So till now we have created the solid elements for the excavation layers, 4 nodal tetrahedral solid elements for the excavation layer as well as for the ground. The next step is creating the retaining wall. The most important thing to note is till now we have used all the solids to create the mesh sets, which means the actual nodal connectivity information, the actual node information. I repeat, till now we have used these solids to create solid elements for the ground or the excavation layers. So the nodal connectivity information is there in every edge of this solid. So after you use any solid to create any mesh, then you can use the extract function of MIDAS GTS to extract the nodal connectivity information in whatever manner you want from these solids which have been previously meshed. So using this concept, I'll be creating my first retaining walls, because in that case I'll be extracting the faces from these solid elements to create the retaining wall. Next, I'll be using the edges that have been imprinted on these solids to create my pile elements. I don't have to worry about the nodal connectivities now, because these solid elements have been meshed and the nodal connectivity information is there in these solid excavation layers. So all I'm doing is I'm just extracting those informations to create my next structural elements, which are my 2D plate elements or my 1D piles or my wheels. As I informed in the starting, we'll be creating these retaining walls as per each excavation layer, by which I mean you don't uh, you don't put the whole retaining wall for the whole excavation ground in one shot, but you put the retaining wall for the excavation one first, then put the structure elements, but thus following the same construction sequence we discussed in the presentation. First excavate the portion and then activate the retaining wall and then activate the structural elements in there. So this is my this represents my excavation 1. Using this I'll be extracting my retaining wall for this excavation. So let's name it wall 1. Next we have we will be using the same extract feature for wall 2. So this will be my wall 2 since it's correspond to second excavation layer. Lastly, we have wall 3. Let's see what we have created. We have created 3 mesh sets representing the walls 1, 2, 3. These walls will be activated corresponding to the excavation of the each layer they represent. So using extract function, we have created the walls from our already meshed excavation solids. Next, we need to model as a pile elements. So use again the extraction feature, but this time we'll be extracting an edge from these solids. We'll be extracting these edges. These edges correspond to the piles which have been imprinted on it. So model element, extract element, but this time from edge. We select all the required edges. Specify an attribute of edge pile, and here we are with the pile elements. Next, we use similar feature to extract our whales. This is my whale 1, which will be activated after excavation 1. Similarly, we have whale 2 at a depth of 9 meters, which will be activated after excavation 2. So let's see again. We have created the whales and the piles of extracting it from the already meshed solids. Lastly, we need to we need to create the strut elements. So for the strut elements, as they will be placed after you have excavated the soil, so you don't need to worry about the nodal connectivities with these strut elements. So we just show the strut elements and then we'll use auto mesh for edge to mesh to create 1D elements for these strut elements. So mesh, auto mesh, using auto mesh edge, and we have struts in here. Number of divisions, let's say 1. Apply. but this is not the required depth of the struts where they need to be placed. They need to be placed at a depth of 4 meter for first excavation stage and 9 meter for the second excavation stage. All we will do is we don't have to create the each strut elements again. We'll be translating this mesh set to the required depths. 4 and minus 5. So we don't need the initially created method. Rename this one as struts 1 and rename the second one as struts 2. But this is not the end of modeling and meshing. Now comes the most tricky part. We have created the H piles, but what about the orientation of these elements? We need to take care of the orientation of these elements, like all the x-axis, they all align in the same direction. So let's see how they align. And all we see is these are aligning in just our random direction. Some of the x elements, x forces are cancelling each other. So we need to take care of this concept and then align all these pile elements in one direction so that the local the elements with different local x-axis don't cancel each other. So we'll align all the elements in such a way that they have a common local x direction and a local y direction. So model, element, change parameter, and we align local axis, select the mesh set, select any base element, first I will increase the size of these. So all we see is all the local x of each element of the piles are now facing in the downward direction, and all the z are in local z direction are facing in corresponding to the global x direction. But let's see the way we want to model the piles. We want to have the piles in such a way that for the piles along the longer length, the local z direction should be in this direction, should be in the same direction as the global y. I will request all of you to focus on the screen because I'll be using this my mouse to highlight the dimension, the directions. So for piles on the along the longer edge, the local z direction should be from bottom to top, and for piles along the width, the local z direction should be corresponding to this. But what we have created is, let's see the top view. The local z direction for along the sides are in the same should be in from top to bottom, but ours are from left to right, and the local z direction for the piles along the sides should be from left to right, and they are corresponding, which means we again need to change the orientation for the middle elements. So model, element, change parameter, and this time we'll apply a orientation and select 1D element filter, apply bit angle of 90, and we apply again. So now we have y-axis going from left to right and z going from top to bottom or from bottom to top. So this was this is this is very important concept when we need to realign all our 1D elements in a particular direction so that the element forces don't cancel each other, because the results similarly same is the case with the whales. The local x forces are cancelling each other, so again we need to align these things in a particular direction. We'll align again. So we have aligned all our strut elements in a particular direction again. Next are our struts. Since we have created only one division for these strut elements, so we don't have to worry about the cancelling effect of these strut elements. The next, and so we are done with our modeling and meshing. The next in the picture is we need to apply the boundary conditions. So first, so let's first apply the ground boundary supports. We use ground support function of MIDAS GTS, and this we simply select all the methods and automatically considering the considering the settings which we had defined in the project setting, like the gravity direction is Z. We will have rollers on the supports, roller supports on the sides, and pin supports at the bottom. Next is we need to create pile supports restraining the rotational degree of freedom. So these are pile supports. We restrain its rotation degree of freedom RZ. Apply. This is very important when it to ensure the convergence using pile elements or beam elements representing piles. So we have created the ground supports. The next are, since we are performing a dewatering semi-coupled analysis, so we need to apply nodal heads as boundary conditions for different construction stages. So beginning with the initial construction stage, these nodal head correspond to the value of their height, the total head. So the value which I will be assigning on each nodal head will correspond to the total nodal head value, which is just the height of the ground level. So this is for the initial. Then we need to, since we are performing a dewatering seepage stress analysis, we need to activate the nodal heads at the required depth of excavation. So we need to activate nodal heads at a depth of 35 meter from ground, or a depth of 5 meter excavation. Let's have 35 total head. Next is for the second excavation stage, dewatering has to be done from 35 to 30. We apply a nodal head of 30 at this point. Lastly, dewatering need to be done to 25. So we have created 3 excavation stages with a depth of 5 meter each, and as well as nodal head at each excavation level. The next is, since I focused it, we need to have impermeable boundary conditions. We need to have impermeable retaining walls. So the next step is we need to create the seepage phase corresponding to each excavation layer. The seepage phase 1 will correspond to only excavation layer 1, seepage phase 2 will correspond to only excavation layer 2, and similarly seepage phase for excavation 3. a very important point which should be noted at this point is these seepage faces are not created on the excavation layer. Rather, they should be created on the ground after these excavations have been done. So we remove these excavations and the seepage faces have to be there to help to account for the impermeable nature of the wall, and we will give a total head of 0 for these seepage faces. So which means giving a value of total head of 0 at these seepage faces, we ensure that there is no uh, seeping of water through the retaining wall. So seepage phase 1, assigning seepage phases is very tricky again. Seepage phase 1 corresponding to my first excavation, corresponding to the retaining wall which will be activated at my first excavation. But this is for the whole depth. All we need to do is we need to activate the seepage phase corresponding to a required depth. So the cheat code I will be using is the curves which we use to create the dividing surfaces. So the first two curves correspond to the excavation stage 1. Since we have activated all the elements, we need to deactivate the rest elements. Let's see again. Oh, we need to perform it again. Let's first remove the extra curves. Hide these. These curves are going to represent help us with assigning these seepage faces. So assign a seepage phase 1. So these seepage phases correspond to only excavation 1. We give a node head value of 0. Apply. Analysis. Remove the seepage phase. Perform the same same methodology for seepage phase 2 and 3. Deactivate the extra elements. This is seepage phase corresponding to excavation 2, and we again give it a value of 0. Last on the list is seepage phase for excavation 3, and we will be performing the same methodology. So we have seepage phase for excavation 3, and we apply it again. So till now we have created the seepage phases for the retaining wall. So, but as I emphasized in the starting, we have to ensure that and at the end of at the end of our whole excavation, at the bottom surface, we need to ensure that the water doesn't seep in. So we again have to provide a seepage phase at the dredge level, or the dredge phase at the bottom of the final excavation at the bottom of the ground after final excavation has been done, so to ensure that the water doesn't seep in through the ground, so which can hamper our project. So this is our dredge level seepage phase. we need to deactivate the extra ones, and we give it a total head value of 0 and we apply. So as can be seen, we had the seepage value with the value seepage faces with the head of 0 at the dredge level 2. This will ensure that no water is seeping through the bottom of the excavation. So we have created the seepage faces also required to ensure the impermeability nature of the retaining wall. Last on the list is we need to apply the loads. For loads, only self-weight will be applied, and the self-weight factor, only self-weight factor will be applied. And this factor will be multiplied by the value of G, which has been defined in our project settings. So all we are left with is our definition of construction stages. So we define a new, this is our initial stage for seepage, and we have a seepage steady state analysis. We'll activate all the original ground surface. We'll activate our nodal head of value 40 and save. Next on the list is we need to perform an initial stress analysis. So since we have activated the elements previously, we don't need to activate them again. All we need to do is we need to activate the self-weight and the ground supports, and we need to clear the displacements. So this will be our initial stage that will be used for our stress analysis, and corresponding to this, the displacements will be used, and the displacements obtained after analysis will reflect the behavior of only each excavation rather than the self-weight component of the ground which was present there, since we have checked the clear displacement option. Next, we install the piles. All we need to do is drag and drop the piles, drag and drop the pile supports at this point. Next, dewatering from level 40 to 35. Since our first excavation stage is going to be of depth of 5 meter, we'll first perform a dewatering steady state analysis, and then we'll perform a stress analysis corresponding to that excavation. So in this, we need to activate our water level at a depth of 35. It is very important to know that in MIDAS GTS, every time you deactivate or activate any element, all the boundary conditions as well as loads will automatically be deactivated with the deactivation of the element. So then we perform a excavation 1. In this, we deactivate the elements corresponding to excavation 1 and activate our structure elements, which will be our struts, wall 1, wheel 1. Save. Next on the list is dewatering corresponding to from a depth of 35 to 30. Activate and perform a seepage steady state analysis. Next is excavation 2. I haven't activated my review boundary conditions or the seepage boundary conditions, which I will be activating at the last in one go. So, and for the second excavation, deactivate the excavation layer corresponding to excavation 2 and activate the structural elements corresponding to excavation 2. So, which will be my strut 2, wheel 2, wall 2. Next we have dewatering for the final excavation. which is from 30 to 25 meter depth, and perform a steady state seepage analysis. Save, and then perform excavation 3, in which we just activate the structural element, which is just wall 3, since we don't have struts or our so-called wheels in that excavation stage, so we just deactivate excavation 3 and activate wall 3. Now we activate all the required seepage phases or the review boundary or the so-called review boundary conditions. Being on the safer side, we will activate the review boundary conditions prior to the activation of the wall. So seepage 1, save, and the next dewatering, seepage 2, save, and the third dewatering, seepage 3, and save again. So we have performed all the required construction stages which need to be made for this semi-coupled analysis. Make a analysis case. And this will be a construction stage analysis type, in which you specify the initial stage for stress analysis, which won't be an initial seepage, but initial stress with a K0 condition. And then you can also take care of the non-linear iteration schemes for different kind of projects, like you can have constant Sifrin method or the secant method. For this, I'll be using a Newton-Raphson method. And we are using a convergence criteria of force norm with a value of 0.001. Lastly, before running the analysis, we need to take care of the stress of the points where the stress, strain, and the seepage results will be computed, to have the nodal values as well as the center values, because just the center values will give me the average values for all the nodes for a particular element. So it's to have a more accurate results, we will check center plus nodes for both stress, strain, and seepage analysis. So everything that need to be done to perform a semi-coupled analysis concerning deep excavation has been done. So all we are left with is solving it. But since solving is going to take a lot of time, for that I'll be opening my previously analyzed model. To discuss the results. And the results, I'll be focusing on what results for each material we will be focusing, like for 2D forces, for 1D element forces, for stresses, for the seepage forces. Starting with a seepage results. We first see the total head values. There seemed to be some problem with the graphic card. Let me check it again. There seemed to be some problem with this graphic card. All we will be doing is we'll be performing an analysis for the previous model again. So this will take some time, and for that we'll be holding a small 2-minute break. and then I'll be discussing my post-processing results. Oh. I believe some of the files are missing, which is causing this problem. So as I said, this was just a problem with the graphic card. So sorry for the delay. So first we'll be checking our uh, total head results. So first we'll be checking the results for seepage analysis. So which are the total head results? The total head results, you can see that initially the value is 40 for all the points, and then with each excavation, the total head values are changing. Rest. Next in the list is we have the pore pressure values. The pore pressure values give us the phreatic surfaces. We can have the zero phreatic surfaces corresponding to each excavation stage. So as we can see is we'll use probe result feature to ensure that we have zero value everywhere. With each excavation stage we have zero value. So at the top of the each excavation layer we ensure that there exists a zero value, thus having a zero phreatic surface as well as zero value for the dredge level. Next, to see the importance of seepage phase, we'll be checking the values of V, X, Y, Z, and we checking on the vector plot. Here I will emphasize what it would have been had there were if there were no seepage phases. As we can see as the water is not seeping through the walls. The water is dripping along the seepage faces to the bottom, and from where since we are performing the dewatering, the water is moving up. So this is the effect of the seepage faces. Had there been no seepage faces, water would have seeped through the walls, and these arrows and the motion of the water can be seen through these arrows. So this was all about the seepage pressure results. We have total head values, the pressure head values, and the velocity values. The next in the list is the displacement values. We check off all the vector plots, the displacements in X, Y, Z. To better visualize these displacements, I'll be using the splice curves, the splice planes. So we can define a new splice plane. Let it be in the Y direction. Okay, A2, and define in the Z direction. That will be let it be A3, and add. So turn the PU to false and click apply. Now on 3 faces we will see how with each excavation the values of displacements are changing. We'll begin with the initial stage, initial seepage, dewatering. Since these are just the seepage analysis results, so there will be no deformation. So this is the first construction stage corresponding to the installation of piles. The next construction stage corresponding to the first excavation. The next construction stage corresponding to second excavation, and lastly the third excavation. The next in the list are my stress results, my total stress results, and my effective stress results. I'll be using a clipping plane again to represent the results. How the stress values change with each excavation can be visualized, and using some of the features like probe results we can actually get the value, and then we can actually get the value, what are the values of the stress at each point, and then we can transfer the values to any of the Excel to use those results for our required purposes. The next in the list are the properties, the results concerning our walls. We need to consider the displacements of these walls as well as the moments in these walls. So beginning with the first one, the displacements. The XYZ. So these walls will be activated in the later construction stage. So we have the displacement values, and changing the filter we can get the displacement in a particular direction. To have the pronounced effect of the deformation, just check on the deformed, and we can see how the deformation changes with each construction stage. Now these deformation values can be used for our required purposes using some of the very nice features of GTS, like on the curve diagram, where you can get the whole value on a selected curve, and then you can transfer these values as diagram or as a table. I'll be using this on the curve diagram how we can save the moment results of the wall or the piles for our required purposes. So these were the deformation results of the wall. Next we have the moment results for the wall at different excavations. But these moment results are just useless. As I told you, we need to be very much precise in the manner we extract the results. So let's see what the problem is. For the walls, if we display the element cross section as axis, they are just going anywhere. There is no particular alignation of the local axis of these plate elements. So to get the output, we need to align all these axes in a particular direction. Then only the result has some meaning. To do so, we'll align all these to a coordinate system. So let it be specify coordinate system, and then we align all these wall elements corresponding to this coordinate system. We can visualize the coordinate system which we have made. So in the properties of wall, we align to this output coordinate system and project to element surface. Okay, now let's see the results. After this thing has been done, the results carry some value. Previously, this is how we extract the accurate amount of information from this from the millions of elements containing information. These are the values of the bending moments of the plate. Next in the list we have 1D elements, which are mainly piles, struts, and wales. So first I will be considering just the pile elements. Talking with piles, the moments, the bending moment, since these are beam elements, the bending moment is of great concern. So these bending moments can be seen, and then the required value can be exported to Excel using on the curve diagram. Here we specify the say 20 divisions. We can get, this is a diagram. Now we can, to get the values in the form of table or diagram, just select table. Now these values of bending moment can be exported to Excel or can be used for the required purposes. Next, the deformation of the piles is also of a great concern in the actual projects. So considering the deformation of piles, we see the deformed behavior of the piles, how these piles behave when the excavations are performed. This is the piles are installed, and this is due to the Rankine pressure or the passive pressure of the earth that is affecting the that is pushing the piles inside. Now we have strengthened the piles using our strut elements, the retaining walls, and the piles have been strengthened. Similarly, we perform other excavation stages. The next on the list are the results of the bending moment results and the deformation results of wale. And clubbing this with the pile, we can see that how the deformation of combined wale and pile structure behave when we perform the excavation. Similarly, for the wales, the bending moment results are of utter importance. and again the values of these bending moments can be extracted as required. You can use either the probe result function that will give you the value corresponding to each element, and you just select the element, and then the value, we can see this value in each construction stage, how the value of bending moment at a particular element changes with respect to different excavations. Or we can also, again, as I previously said, use on the curve diagrams and export those values to Excel and use it for required purposes. Last on the list are our struts. So let's activate the struts. For struts, the axial forces are of utter importance. We need to be aware of the axial forces that are present in the stress at a given time, and then we can further perform an continuity analysis in which we can deactivate, we can remove one strut and then see how the structure behave, how the excavated earth along with the structure elements behave when a particular strut is not there. So this is very important when we need to perform as I previously said, when we need to perform a continuity analysis. So the behavior, the strength of the effect of one strut on the uh, uh, whole family of structure elements present in that excavated ground can be seen in that continuity analysis, in which you just remove a particular strut and then perform the analysis. All you need to do is you need to have an extra construction stage, just deactivating a particular strut and then comparing the results. So this was all about the modeling, meshing, extraction of results, and how different modeling techniques when it comes to deep excavation, with the problem concerning that graphic card. I'm again sorry. So this was all about my presentation today. I'll be entertaining questions, so if you have any queries. We have a question from Mr. Abid Ali. What difference in results can be expected if the seepage phase is assigned to the wall instead of the ground surface along excavation? Mr. Abid Ali, I believe that the results in both the cases are going to be approximately the same, because all we are having is but in that case, you need to activate the wall in that seepage test analysis, not in that construction stage test analysis where you are activating the wall, because the seepage phases can be reflected only in uh, seepage steady state analysis. And if you want to follow that procedure, you need to activate all the structure elements along with seepage phases in a particular element, particular construction stage, which will be my steady state seepage. And then in the next construction stage, you make a dummy construction stage to adjust the stress level in the ground. And with that thing, we can see those results. We have a question from Mr. Abid Ali. What is the criteria for aligning the element cross section for wall, in which direction should be aligned? There is the only criteria we have for aligning the cross section is we want the maximum, the criteria which I followed is, and which is generally followed when it comes to dealing with GTS, is you want to have the major moment as my. So have my along a particular on a particular face in a particular direction. So all I mean to say is all the x and y will be on the face of the plates. So these alignment should be done in such a way that the major moment when we see in the result should be my rather than mz. So having that thing in mind, you can make and yourself your own criteria for aligning the cross section. There is no hard fast rule, because if I have my if I have in mind my if like my mz is my major moment, so corresponding to that I will do the alignment in which the results reflect that mz is my major moment rather than my. So in the end, concluding, there is no special criteria. All you need to do is you need to align all the elements in a particular direction, and you have to then alter the results accordingly. Okay, sure. I will explain that thing in the model. Mhm. The element coordinate system which I applied in my models are, let's apply a new element coordinate system. So if if I have a particular element coordinate system, say, and this is my origin and this is my y. This element coordinate system having all the xy in a particular direction, and in this thing mxx is going to be my major moment rather than myy. And if I align all these elements according to this scenario, my mxx will be my major moment. So but if I go for the vice versa, having myy as the major, so this way my myy will be major for my plate elements corresponding on these two faces, and my mzz will be major corresponding to these two element faces. So you need to check the results with respect to their orientation. First you need to consider the moments. If you need to consider the moment in these two faces, you need to consider myy, and if you need to consider the moments in these two faces, you need to consider mzz. So this is the way you keeping this thing in mind, you can extract the results, whatever results you want. uh, if it's a curved, so the only criteria you follow is you have the local axis, all the axes are aligned in along the local axis of the tunnel. So if you have three perpendicularly aligned tunnels, you check for the results for mxs or myy separately for each tunnel. You have separate coordinate systems for each of them, which I will be focusing in my coming educational webinar on tunneling. And then you align all the coordinate system as in such a way that the x-axis are aligned with the local axis of the tunnel. We have a further question. From Mr. Abed Ali, if I want to model a leakage in the wall due to improper joints between the excavation stages, how can that be done? All you need to do is have some seepage flux along with seepage faces. You could also use the nodal flux values with specifying some of the flux over the walls, but in that case the results won't be as accurate as if you use seepage flux with a specified value that will represent the leakage of water from those walls. So I believe this was we don't have any other question. So in case you have further questions, please I will be happy to help you. Please email us at esupport. Email all your queries at esupport@midasit.com. Thanks for your time. Thanks for your attention. If you have further queries, if you want any further information concerning deep excavation, feel free to leave a mail on esupport@midasit.com. Thanks a lot.